Hello, we're now at the point of section 1.2 where we're going to talk about connected and disconnected graphs. So a connected graph is just a graph where there is a walk joining any pair of vertices. So for example, in this particular graph, if we look at all the different pairs, A and B are connected by a walk of length 1 right there. A and C are connected by a walk of length 1. A and D are connected. B and C are connected by a walk of length 2. So are B and D, and so are C and D. So this is connected graph because we can basically travel from one vertex to any other vertex in the graph. And we've defined our connected graph as being a walk between any pair of vertices, but we know that whenever we have a walk between two vertices, we also have a path. So we could alternatively just define this as a path between any pair of vertices. And to go along with that, we have disconnected, which means the opposite of that, which is that there exists a pair of vertices that are not joined by a path or a walk. So as I say, those are kind of interchangeable in terms of the definition. So for example, if we look at this graph, which has vertex set V1 through V7 and all of our edges here, this whole thing is a graph, but we can see that we've got kind of one subgraph here from vertices V1 to V5 that's separated from our subgraph induced by V6 and V7, and there's no way to get from a vertex on the left here to a vertex to the right. So this is a disconnected graph, and each of these pieces is referred to as a component. So visually, we can see that our graph kind of has two separate pieces, and there's no one way to travel from one to another. So in small graphs, it's pretty easy to decide whether or not your graph has more than one component or is disconnected. And of course, if we look at another example, how we draw the graph doesn't matter. So here, even though kind of visually we have two parts overlapping, this subgraph induced on vertices U and V is disconnected from our subgraph on vertices W, X, Y, and Z because we could just take that piece and kind of move it somewhere else. Now, in larger graphs, we might not have that kind of visual cue of looking at the graph and seeing different parts. So there's some other ways we can think about connected and disconnected. So one definition is for what's called a maximally connected subgraph. So if we have a particular graph that is, say, a disconnected graph, maybe it has a few different pieces and we can actually kind of draw it with different parts to it. We can look at a particular subgraph. Say we look at the subgraph induced by S, T, and V. So if we look at that particular subgraph, S, T, and U, those three vertices and two edges would give us an induced subgraph. So that induced subgraph in green is connected. But it's not a maximally connected subgraph because we could make it bigger. We could add in vertex R to those other three vertices and get a bigger induced subgraph that's still connected. However, if we tried to add another vertex, either say Q or V, and grow our induced subgraph, we suddenly become disconnected. So this green induced subgraph is considered to be a maximally connected induced subgraph. We can't make it any bigger. And similarly, our subgraph over here on VWX, that's maximally connected. The yellow graph on its own is a connected graph, but we can't add anything and stay connected. And then finally, we have our final graph over here, Q, which is just a single vertex. Again, it's a maximally connected subgraph. So we can use that definition for what's called a component of a graph. A component is just a maximally connected subgraph. So each of these parts, Q, RSTU, VWX, is a component. So this particular graph has 3 components. And again, visually you can see that you've got these 3 separate pieces that aren't connected to each other. So I just realized I skipped over this slide. So we have the definition of a graph being connected, but we can also talk about pairs of vertices being connected. So, again, we can think of them being connected if they're connected by a walk, but we know if there's a walk, there's also a path. So again, we have these kind of 2 definitions that 2 things are connected if they're joined by either a walk or a path. You can use either one. All right, now we come to Theorem 1.7 in the textbook, which talks about relations, and that if we define what's called a relation between 2 vertices, if they are connected to one another, remember that just means there's a walk or a path between them, that it's equivalence relation. So if you haven't been exposed to relations before, here's the easy translation of an equivalence relation. In this context, there are kind of 3 things that we want to take out of it. The first is that every vertex is connected to itself. That's what's called a reflexive property, that an element is related to itself. So if we define a relation up here as being vertices connected to each other, the reflexive property is just referring to be connected to yourself. So for people who are familiar with equivalence relations, that's the reflexive property. And we know that connected just means there's a walk or a path, either can use either one, between 2 vertices. So kind of trivially, for a vertex to be connected to itself, we've got a walk of length 0, or a trivial walk. So that's a reflexive property. Now the second property for connected is that if U is connected to V, then V is connected to U. So if there's a walk from U to V, we can just reverse it and take that walk from V back to U. So that's what's called a symmetric property. And the third property, when we're talking about what's called this equivalence relation, is the transitive property. So if we have 3 vertices, if X is connected to Y and Y is connected to Z, then X will be connected to Z. So that's the transitive property. So if, again, you're unfamiliar with this equivalence relation definition, you can just replace Theorem 1.7 with these 3 statements, and it's saying the exact same thing. So you can see that if we were trying to prove each of these 3 statements, 1, we don't really need to prove anything. That's a trivial walk from a vertex to itself. Number 2, just reverse the direction of your walk, and you've proven number 2. And number 3, well, let's have a look at proving number 3. So here's our problem. Suppose we have 3 vertices, x, y, and z in some graph G. We want to prove that if x is connected to y and y is connected to z, then x is connected to z. So we're going to use a direct proof. So remember that if we have a direct proof and we're trying to prove an implication, P implies Q. So here's our P, x is connected to y and y is connected to z. That would be P. And then the x is connected to z would be the Q part. For a direct proof, we assume that P is true and then we use a number of true statements based on that assumption to conclude that Q is true. So in a direct proof, we're going to start with supposing P is a true statement. So suppose X is connected to Y and Y is connected to Z. So that's our starting point. So what does that mean? Well, what's the definition of connected? That there's a path or a walk, can use either one, between X and Y, and then there's a path or a walk between Y and Z. All right, so here, let's use path. That's just as easy. So there's an XY path, we'll call it P, and a YZ path, we'll call it Q. So what does that mean? Well, just picture what would happen. You start at some vertex X, and you keep going until you get to vertex Y. So there's P, and then we can keep on going and continue on from Y to Z along path Q. So we can go from Y to Z. Now maybe we use some of the same vertices and edges that we found in P, but eventually we'll end up at Z. So we can see that if we just, take P and follow immediately with Q, we might not get a path from X to Z, but we get a walk from X to Z for sure. So here's how we can put this in words. If we immediately follow path P from X to Y with the path Q from Y to Z, and in terms of notation, we just note that we don't repeat Y, we just keep going. So it would, look like X until we hit Y, and then we'd go from Y to Z, and this portion of things would be P, and this portion of things would be Q. So we're just going to stick them together like that. And the result is an XZ walk. Now, if we're using a path between the two things as our definition of connected, then it follows from the theorem we proved in the previous lesson that G contains an XZ path. So that proves our transitive property. We've proved that X is connected to Z. So perhaps I should have finished off with that final sentence, therefore X is connected to Z, and that would be the end of the proof. All right, so our final result for this video is theorem 1.8. What does it say? It says that if we have a graph G of order at least 3, we'll start with that. If G has distinct vertices X and V such that U and V, such that G minus U and G minus V are both connected, then G is also connected. So this is going to be another direct proof. And we can think about, if P then Q, or P implies Q. So this whole part here is the if. So with the direct proof, that underlined portion of things, that's what we're going to assume is true. So we start off with our proof that we're going to suppose that sentence. G has distinct vertices U and V such that G minus U and G minus V are both connected. All right. So we want to think about what that looks like exactly. So we've got this kind of unknown graph G, so we're just going to have to be very general with our argument here. We've got some big graph G, and maybe we'll just say G lives inside this rectangle. We've got a vertex U, I'll put over here on the left, and a vertex V over here on the right. We know for any graph, no matter what it looks like, we can, kind of put the vertices anywhere on the plane in our drawing. Now, it's got at least one other vertex, so there are some other things in the graph. So I'm going to represent this dotted circle as the rest of the graph. And I know that it has at least one vertex, and maybe just kind of for argument's sake, I could pretend there's a few more. Now, I don't know what things look like inside of that circle, but I know there's vertices and there's probably some edges. Now, U is going to be connected to some things in that circle, and V is going to be connected to some things in that circle. So here's my kind of general picture of what my graph looks like. So let's give the vertices kind of in the middle here. We'll name that set of vertices. Maybe we'll call it R for the rest of the vertices. So my vertex set I can think of as being U, V, and the rest. So now I can think about these two subgraphs, G minus U and G minus V. So let's think about G minus U first. So that would be this part of the graph. So remember, I'm just going to delete U and anything it's any edges it's incident with. So I'd have this, what's inside my green box here. Now I know that G minus U is connected. So all the vertices inside that green box are connected to each other. So I could pick, two vertices inside my R circle, and they're connected to each other by vertices in the green box. So they could be kind of connected to each other somehow within my R circle, or maybe to get from one to the other, I'm going to have to use V. I'm going to have to come out here and get from one vertex to the other. But there's some way to get from one vertex to the other for every pair of vertices in that green box with only using edges in that green box. Everything inside the green box is connected. Now we could do the same thing and look at G minus V. And G minus V is connected, so everything in that pink box is connected. And again, the vertices, kind of inside the R circle are somehow connected to each other, in some way. And U is connected to everything in that R circle. And because all of those things are connected in G minus V, and they don't, they don't use the V vertex, they're just using things inside the box, all those connections still exist in our full graph G. So we can put that into words in our proof here. We have our original assumption. Since G minus U is a induced subgraph of G, if a pair of vertices are connected in G minus U, they're also connected in G. So therefore, in the graph G, every pair of vertices in this particular vertex set, which is just all of our vertices and take out U, every pair of vertices is connected. And by a similar argument, every pair of vertices in V of G minus V is connected in the bigger graph G. So it's going to suffices to show that U and V are connected. So that means that's all that's really left to prove, that in the bigger graph G, U and V are somehow connected to each other. Because remember, to show that G is connected, we have to show that every pair of vertices in G are connected. So, to kind of see why that is true, you're thinking about comparing, all the different pairs to see if they're connected. So, when you think about your different options, you could see if U is connected to everything in the set R, which it is because G minus V was connected. So U and R were in that graph. If you want to check that V is connected to everything in R, we know that's true because G minus U was connected. So we took out U and we looked at things in V and R when we looked at G minus U, and that worked. So, those two situations worked. We also know that if we chose two vertices out of R, those are connected because both G minus U and G minus V left this set R, and everything was connected to each other in each of those subgraphs, so they're connected to each other. So the only one left, of all these kind of different ways we could um, choose a pair of vertices is if we choose U and V. So that's what's left in the proof, that showing U and V are connected to each other. So now let's prove that U and V are connected to each other. So what we do is we just choose any other vertex X out of the graph other than U and V. And we know there's something to choose because G had at least 3 vertices to begin with. So what we have is we've got U and we've got V, and then we've got some vertex X in that R set. So we know, and we've already kind of gone through all the possibilities already, that U will be connected to X because U is connected to everything in that R set, and X will be connected to V. So somehow we can get from U to X, and then we can get from X to V somehow. So by that transitive property that we talked about earlier, we know that U is connected to V. So there's where our theorem 1.7 came into play. All right, so that is the end of the proof because we've proved that every pair of vertices is connected. A pair is connected. So this is a little bit different presentation than in the book, but hopefully you can see that all of the ideas are the same. And that is the end of our first video for this lesson.